Suppose we want to solve the following problem using the graphical method. We have two decision variables, x1, x2, and we actually don't know what this problem exactly represents, this model, what kind of problem it is solving. But we know we're maximizing a certain function, x1 plus 4x2, and we have 5 constraints, 3 of which are complex constraints, and 2 constraints, 4 and 5, are simple limits on decision variables. Notice that first constraint looks like a minimum requirement for x1 plus x2 to be at least 3. Constraint number 2 looks as if it is some kind of resource constraint. 2x1 plus 5x2, this is some kind of consumption, must be less than or equal 20. And the third constraint is neither resource nor minimum requirement. It actually says that this has a negative coefficient for x2, right? x1 minus 2x2 less than or equal to 0, which actually you could rewrite as x1 less than or equal to x2. So it says maybe, some kind of activity x1 must be smaller than 2 times the value of activity 2. This is the 3 complex constraints, and then we have simple limits. We know x1 may be maximum 6, that's constraint number 4, and then x2 has to be at least 0. And notice this is non-negativity. Notice there is no lower limit on x1, so x1 could be positive, could be 0, or it could be negative. So how do we plot it? I prepared here the beginning of the drawing, straight lines for axis and some kind of units. Now, if you plot your feasible region and you end up with something that is very small, like for example, you plot it like this and you end up with a feasible region that looks like this, and this is the feasible area, it's always a good idea to redraw the whole region larger. Change the unit so that it is larger. If you start drawing and then you discover, oh, one of my constraints crosses from here and goes there and somewhere far away, and I cannot even plot the feasible region. The feasible region goes on here to the right, right? And then again, it's a good idea to redraw it, but now smaller. So in this case, I've chosen already the units that will allow me to plot this feasible region reasonably large, not too small, not too large. I will always put the first variable on the horizontal axis, so this is going to be x1, and the second on the vertical, this is going to be x2. I will also mark unit 0, 1 at 1, and then of course I will put additional units. And notice, because x1 can be negative, I'm actually allowing here for negative values for x1, so there will be -1 and so on to the left. Okay, let's plot the first constraint. The first constraint, x1 plus x2 equals 3. If you turn it into equality, you'll find out 2 points that satisfy it are 0, 3, and 3, 0, 2 easy points, right? We can determine. So I will use a ruler and I will find the points. Points 3, 3 are here, right? These are the 2 points, and I will try to plot a line that goes through those points. Right? So this is the line where values x1 plus x2 is equal to 3 with equality. Now if I want greater than or equal in this constraint, then I need to see points that are above the line and to the right. So this is my constraint number 1. And now I will need constraint number 2. Let's erase this. So constraint number 2 is 2x1 plus 5x2 equals 20. So we can try values x1 0, then 5x2 equals 20. So that means x2 is equal 20 over 5 equals 4. So x2 is 4. And then if I try 0 for x2, 2x1 equals 20, that will be x1 equal 10. So I need to find where x1 is 10, 4, 5, 6, 7, 8, 9, 10 is this point. So here, 10, 0, the line will cross the x1 axis, and 0, 4 at 4, the line will cross the x2 axis. So now I need to again plot a line that crosses these 2 points. Okay. Now we need the third constraint. The third constraint, because it has a right-hand side 0, is going to be an interesting one. When you have right-hand side 0, x1 minus 2x2 equals 0. If you try our standard way of putting 0 for x1 and determining x2, you will see if x1 is 0, 2x2 must be 0, so x2 is also 0. And then, of course, if you try x2 equals 0, then you'll find x1 is equal to 0. Actually, you determine the same point twice. So that's not what we want. We want 2 different points, not the same point twice. So what I will try is I will try to put another value, let's say for x2, just because x2 is then multiplied by 2 will give me some nice integer number for x1. So let's say if I try 3 for x2, then it's x1 minus 2 times 3 equals 0. So x1 is 6. So I will have x1 equals to 6. And now that's a different point, right? I have 2 points. One is 6. 6 is here. 6 is here. So somewhere here I need, right? And then 6, 3 will be somewhere here, right? So I will need a line that crosses 0, 0, that goes through 0, 0, and through point 6, 3. So this is going to be somewhere here. Somewhere here. Let's try to make it more accurate. Somehow this ruler, okay, there. Okay, this is the line. Okay, and again I will see that which side, this is where the points are equal to 0, x1 minus 2x2 is equal to 0. Well, now I want to go back to less than or equal. So now I cannot be sure whether it will be above or below. You might be thinking if it's less than or equal, then it's going to be always below the line, like we could have said for constraint number 2, it's going to be below the line because it's a constraint with positive coefficients only. Or for constraint number 1, it is above the line because it's greater than or equal, right? However, this constraint with 0 on the right-hand side, you cannot conclude the same way because it's very easy to actually transform this constraint into equivalent format. It's x minus x1, multiplying it by minus 1 to x2 would make it greater than or equal to 0. This is the same constraint, just both sides were multiplied by minus 1. Now it's a greater than or equal constraint. So why would you conclude from the sign whether it is above or below? When you have negative coefficients, you cannot use the same conclusion. So you cannot assume less is below or greater is above. So what we're going to do, we're going to test a point. Remember, every constraint which is greater or less than or equal, right? Either greater, less than or equal, or greater than or equal. Every constraint of that form will have one of the sides will be feasible. So this constraint, if this is the line, either this side will be feasible or this side will be feasible. So, and now if one side is feasible, all points on this side are feasible, and all points on the other side are infeasible. So if that's the case, I can just test one of the points. Say, right, I'll test a point here, and if I find it is feasible, that means all points must be, right? If it is feasible, all points on this side must be feasible, so that's the feasible side. If, however, I find out that this point is not feasible, then that means the other side is the feasible side. Right? So let's try and do this for our constraint x1, constraint number 3, x1 minus 2, x2 less than or equal to 0. So if I, let's say, try point 30, this is the point, and I just say x1 minus 2, x2, right? I'm plugging in 30, so 3 for x1, and minus 2 times 0, so that gives me 3. But the constraint said less than or equal 0. This is not less or equal 0, it is greater, so it's not satisfied. So this point is actually not feasible for this constraint. So what that means is that below the line, points are infeasible. That means then that the points above the line must be the feasible constraints, feasible points for constraint number 3. So we've done constraints 1, 2, 3, and now all that is left is the simple limits. x1 less than or equal 6, we're going to look at this constraint, x1 less than or equal 6. So we need to go to x1 equals 6, which is here, and less will be to the left of it. So that's constraint number 4. And 5 is simple, we don't even have to draw anything, because 5 is the horizontal line, right? And the points above this line, right, x2 greater than or equal to 0, are on the x1 axis and above. So now I can say the points that are feasible are above the x1 axis. That is constraint number 5. So we have all 5 constraints, and notice if you take common set for constraints 1, 2, and 3, you will obtain this triangle, right, somewhere like this. Within 1, 2, and 3, these are the feasible points. Right? So this triangle, including the boundary, is the feasible region for constraints 1, 2, 3. Now let's see what happens if we add constraint number 4 and number 5. Well, nothing changes, because constraint number 4 is already satisfied by all the blue points, and constraint number 5 is already satisfied by all the blue points. So actually constraints 4 and 5 are redundant constraints. We don't need to consider them. Right? They are always satisfied. If constraints 1, 2, 3 are satisfied, then constraints 4 and 5 will always be satisfied. Okay, now the question is, what is the optimal solution? These are feasible points. We need to consider the objective. The objective is here. We maximize x1 plus 4x2, right? So we can again plot the line of the objective. We can see we have actually 3 corner points which we could determine. So one way would be to determine point A, B, and C. Because it's a region that is closed from all sides, one of those points, at least one of them, has to be an optimal solution. And maybe if there are multiple optimal solutions, there will be more than one corner point optimal. But I'm going to use the level curve method. So let me use some red color and try to plot level curves. So let's say if x1 plus 4x2, I'll make it equal to 4. That's a nice, easy calculation. I chose this number, right? You can choose any number as long as it is going to be visible on this picture. So if I did this, if x1 is 0, then x2 will be 1. And if x2 is 0, then x1 is 4. The points are here, 4, 0, and 0, 1. And I need again to plot a line that crosses those 2 points. So this is the level curve, right? And now I need to take it, right? This is for value 4. And it's actually also interesting if I try value 0, right? Then I will be crossing point 0, 0, right? Because for value 0, 0, 0, 0, it satisfies x1 plus 4x2 equals 0. So I can actually plot this line. I could calculate other points, but because this ruler keeps the same slope for me, I can just plot the same line with the same slope that crosses point 0, 0. So I have now here a value 0. So I know if this is 0, objective value 0, this is the objective value 4. If I'm maximizing, all I want is to take it up, right? Up to the right, slightly to the right. So where is it going to be optimal? Is it going to be point A? No, because above point A, above the line that crosses point A, I can still find better solutions, right? If I go further to point B, is this optimal solution? No, because there are many actually points above point B on higher lines, higher level curves, right? If I go to point C, oops, I lost the slope. If I go to point C, right, and I cross point C, right, if I cross point C, this is where I will see no better points. There is no feasible points in this area, right, and only points here in this area above the last red line that I put on this picture are better objective values. So that means C is the last point that gives me the highest objective function value, and therefore C is my solution that I'm interested in finding. So let me try and determine it. So how will I find it? I need to calculate it accurately, right? You might be tempted to read it from the graph. However, it's going to be fractional. You see x2 will be somewhere around 4 point something, and x1 will be somewhere around minus 1 point something. I'd rather not read it from the chart because it might be inaccurate. How do we find point C, right? So point C is an intersection of constraints 1 and 2. So I need to focus on constraints 1 and 2, turn them into equalities. So it will be x1 plus x2 equals 3, and 2x1 plus 5x2 equals 20. And I need to solve this set of equations. Let me take x1 equal 3 minus x2 from the first, and then plug in for x1 in the second equation or equality. So it will be 2 times, and x1 is 3 minus x2 plus 5x2 equals 20. That's the second equation where I substituted for x1 3 minus x2. So that's 6 minus 2x2 plus 5x2 equals 20. So this is 5 minus 2x2, that's 3x2 equals 20 minus 6, that's 14. So x2 equals 14 over 3, which is 4.67, slightly rounded, right? It is actually more accurately 4 2/3. Okay, and then x1 will be from this. x1 is 3 minus x2, which is 3 minus 4.67, which ends up being negative, minus 1.67, right? It's actually minus 1 2/3 if you want absolute accuracy, right? So does this make sense? Let's check. 4.67, yes, we expected x2 to be somewhere between 4 and 5, and the same thing for x1 minus 1.6. Yes, we expected x1 to be somewhere minus 1 point something, right? So check. So now the optimal solution, we determine it as x1, x2. Remember, solution is the values of decision variables. It is minus 1.67 and 4.67, and we still need to plug in this into the objective. So into the objective, optimal objective value is x1 minus 1.67 plus 4 times 4.67, right? If you do the calculations with those numbers, you'll actually get something around 17.01. However, if you use the exact values, you would find out that in fact a more accurate value is exactly 17.0. So optimal objective function value is 17. So this level curve is on the line 17, giving a value 17, and C is the only point that provides 17 units of objective function value. This is the optimal solution, and this is 17. Had we used the corner point method, right, corners, we could have determined corners A, B, C, right? And then we would find objective function values for each of them. A is actually an easy point. If you determine, you would find out it's 2, it's 2, 1, 2 and 1. C, we have determined it to be minus 1.67 and 4.67, and we found out the objective value is 17. For 2, 1, plugging it in, the objective value is 6, much worse. And then B would again require solving system of equations, so we would have to find it here, and we would find the objective value, but definitely this would be less than 17, and then you would find out that this is maximum, and therefore optimal solution is point C, right? This is if you use the corner point method. You can use either of those methods here because the feasible region is a closed region, bounded from all sides. So this way we solved this problem. We found the optimal solution, and notice this was the case where values for one variable, in this case, were allowed to be negative. X1 wasn't limited by 0, right, to positive or 0. It was allowed to have any values, positive, 0 or negative, and the other constraints actually also allowed some negative values down to minus 1.67, and it happened that this is the optimal solution.